So we will see pumping lemma for context-free languages. Okay. Today is Rocky, so my hands are full of Rockies. Okay. Don't lose your focus. Okay. Pumping lemma for context-free grammars. Okay. So what is pumping lemma is? It is a negative test. It is a negative test. Okay. Let us say this is pumping lemma, a wall. Let us say this is a pumping lemma. Now, if a language passes pumping lemma, let us say there is a language L1 which passes pumping lemma, then the language may or may not be, may or may not be context-free language. If there is a language L2, if there is a language L2 which fails pumping lemma, if there is a language L2 which fails pumping lemma, then we can say that the language L2 is not context-free language. So pumping lemma is a negative test. It is used to say that a language is not context-free. It is not used to say that a language is context-free, right? So anyway, we have seen a lot of examples, a lot of questions about whether a language is regular or not, whether a language is context-free or not. So we have seen a lot of them, right? So I don't think that you need really pumping lemma to prove that a language is regular, or to prove that a language is not regular, or to prove that a language is not context free. We have seen a lot of examples. I given you a lot of rules, right? In exam, don't really use pumping lemma, but then it is in the syllabus. So we will see what pumping lemma is, but then in exam we are not going to use pumping lemma. Okay, in exam we will not use pumping lemma. Okay, in exam we will not use pumping lemma. Okay. So let me write down what pumping lemma is. Okay. So this is context free language 4, CFL 4, lecture 4, and we were discussing context free languages, and today also we will discuss context free languages. Before I start the class, please join my Telegram channel. This is the QR code for my Telegram channel. If you have not joined Telegram channel, please join it here. I will be doing a lot of activities in Telegram channel. You will get a lot of updates on Telegram channel. Okay. Okay. Now, Jitendra Malik. Jitendra Malik, hailing from Madura, Jabalpur. He came from a modest Indian academic setting with no elite pedigree. He did his BTech from Kanpur, followed by MS and PhD in computer science from Stanford University. He became a leading researcher in computer vision at UC Berkeley, developed foundational algorithms that shape AI imaging across the globe. He revolutionized how machines interpret visual data. His academic legacy influences self-driving cars, robotics, and healthcare imaging. He is a hero for me. He is an Indian and he is a hero for me, and he should be the hero for you. Jai Hind. Okay. So let us now see. Let us now see pumping lemma. Okay. Let us now see pumping lemma for context-free languages. Okay. Let us now see pumping lemma for context-free languages. Pumping lemma for context-free languages. Just write down the definition as I say. I'll explain you it later. Okay. Let L be a context-free language and W belongs to L. W belongs to L such that mod W is greater than or equal to N. mod w is greater than or equal to n for some positive integer, for some positive integer n, for some positive integer n, then w can be decomposed as w can be decomposed as w equal to a b c d e such that point number 1 bd is not equal to epsilon, point number 2 bcd length is greater than, less than or equal to n, point number 3 for all I greater than or equal to 0, string a b power I c d power I e is also in L, right? So what does this statement actually mean is, I'll take an example and I'll show you. Okay, I told you that pumping lemma is used to find out pumping lemma is used to find out that a language is not context free, Pumping lemma is used to find out that a language is not context free, right? So I will take an example. What does the pumping lemma say is, let us say the example is L equal to a power n, b power n, c power n such that n is greater than or equal to 1. Okay, this is the language, right? Now if I take a string a, b, 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 c, 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 right? What does pumping lemma say is, you pump it at two places equally, then the resulting string should be in the language, right? Let us say I pump here yes and I pump here. Pumping means repeating. Okay, if I repeat yes, what will happen here? A, 4 A's will come. What will happen here? C, 4 C's will come. 4 A's will come and 4 C's will come, right? So the resulting string is not in the language. You may think that you can pump somewhere else. Okay, A, B, 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 C, 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 right? Now, if I pump it here, and if I pump it here, you may think that we are going to generate extra number of A's and B's. But the problem is, if I pump once here, I will get AB, which is not in the language. If I pump once here, I will get BC, which is not in the language, which means using pumping lemma, we may be able to say that a language is not regular. Using pumping lemma, we may be able to say that a language is not regular, but we will not be able to say that, using pumping lemma for context-free languages, we may be able to say that a language is not context-free language, but we will not be able to say that a language is context-free. But in the GATE exam, the questions will be whether a language is context free or not. So you have to be thorough with what examples we have done. Don't rely on pumping lemma. You cannot prove it in the exam and it will take hell a lot of time, but it is in the syllabus, that is why I am covering it. Okay, it is in the syllabus, that is why I am covering it. So for a given language, there can be any number of grammars. For a given language, there can be any number of grammars, G1, G2, G3, so on, Gn. For a given language, there can be any number of grammars. Out of all these grammars, some are more convenient. Some are more convenient for parsing. Some are more convenient for parsing. We will see what they are. Before going ahead, I want to do some small topics. One is elimination of epsilon productions. Okay. So I want to do simple topics first, then we will go to important and interesting context free grammars. Okay. So first one is elimination of epsilon productions. Elimination of epsilon productions. Okay. How to eliminate epsilon? Why to eliminate epsilon productions? Sometimes what happens is sometimes epsilon may not be in the language. Sometimes epsilon may not be in the language at all. Sometimes epsilon may not be in the language at all. Sometimes epsilon may not be in the language at all. Sometimes epsilon may not be in the language at all, right? But in the grammar, there may be epsilon productions. There may be epsilon productions of type. There may be epsilon productions of type A derives epsilon. Sometimes epsilon may not be in the grammar at all, but then there may be epsilon productions of type A derives epsilon. There may be epsilon productions of type A derives epsilon. Okay. Sometimes epsilon may not be in the language at all, but in the grammar there may be epsilon productions of type A derives epsilon. Right. In such cases where epsilon is not present in the language, in such cases we can eliminate epsilon productions. We can eliminate epsilon productions altogether. We can eliminate epsilon productions altogether. We can remove epsilon productions altogether. For example, if I say there is a language like this, for example, if I say S derives ASB or AAB and S derives A derives epsilon and A derives epsilon. Okay. So here if you observe it, A derives epsilon is there, therefore A is nullable. We say that A is nullable. A derives epsilon, so A is nullable. Right? But then if you see in the language, there will be no epsilon. You cannot generate epsilon in this language. S is not nullable. You cannot derive epsilon from S, but you can derive epsilon from A. Right? Then what we can do is, you can substitute this epsilon here and you can eliminate this. You can substitute this epsilon here and you can eliminate this altogether. Then what do I get? The grammar? The grammar will be S derives ASB or AB. S derives ASB or AB. S derives ASB or AB. The grammar can be simplified. Right? Understood this? What I am saying is, sometimes epsilon is not in the language at all, but in the grammar there are epsilon productions, but we can eliminate those epsilon productions altogether. Right? But sometimes what happens is, the epsilon will be in the grammar. Sometimes epsilon will be in the language. Sometimes epsilon will be in the language. In those cases, we cannot eliminate epsilon productions all together. We cannot eliminate epsilon productions altogether. In those cases, we cannot eliminate epsilon productions altogether. Right. At least there will be one epsilon production. At least there will be one epsilon production. At least there will be one epsilon production in the grammar. At least there will be one epsilon production in the grammar, right? What is that epsilon production? S derives epsilon. At least the starting symbol derives epsilon should be in the grammar, okay? When the epsilon is in the grammar, when the epsilon is in the language, in those cases, we cannot eliminate all the epsilon productions altogether. At least there will be one epsilon production in the grammar. S derives epsilon, right? Now let us see how to eliminate epsilon production. Now let us take some examples and see how to eliminate epsilon productions from a grammar. Okay, I'll give you some grammar. Let us see how to eliminate epsilon productions from the grammar. S derives AB, A derives A or epsilon, B derives B or epsilon, right? So whenever any grammar is given, you have to find out if epsilon is present in the grammar or not. When will epsilon be present in the grammar? When S can derive epsilon. When S can derive epsilon, we can say that epsilon is present in the grammar. Here you can clearly see that S can derive AB, S can derive AB, A can derive epsilon, B can derive epsilon. Therefore, S is deriving epsilon, so epsilon is in the language, right? But we need a systematic method to find out whether epsilon is. We cannot use this method. In the exam, it will be too confusing to use this method to find out whether S is deriving AB. If there are more productions for S, it will be even more difficult. So I'll give you a simple trick, right? So first find out what are all the nullable variables. Right? So what do I mean by nullable variables is a variable is nullable if it derives epsilon, right? So A derives epsilon, therefore A is nullable, and B derives epsilon, therefore B is nullable, and S derives AB, both A and B are nullable, therefore S is also nullable, right? Now we got that S is nullable. Right? Therefore, we cannot eliminate epsilon productions, all the epsilon productions. At least one epsilon production should remain, which is S derives epsilon, right? So, at least one epsilon production should remain, S derives epsilon, and all the remaining epsilon productions can be eliminated. See this? Here A is nullable, here B is nullable. So, when A is nullable, go to every production where A is present, write with it, write without it, right? So, here the A is present, right? So, write with it, AB, and write without it, right? And now here B is present, right? So, write with it and write without it. Here B is present, so write with it and write without it. So I have written with it, I will write without it. Write with it and write without it. Right? And here also do the same thing. Write with A, write without A. A derives A, write with two A's, remove one A, and remove the other A. Altogether. Write with it, write without it. Write with this A, write without this A. Write with this A, write without this A. Right? Now similarly, B also is nullable. Therefore, write with it and write without it. So I am writing with B, and now I will remove one B and now I will remove the other b also, and now I'll remove the other b also, right? So this is the grammar we got, where we have eliminated all the epsilon productions except one. Why except one? Because epsilon is there in the language, you cannot eliminate it. Without having epsilon production, you cannot generate epsilon in the language. Epsilon is in the language. Why epsilon is in the language? S is nullable. That is why epsilon is in the language. S is nullable. That is why epsilon is in the language. Now let us see one more example where we can eliminate epsilon productions. Okay. So let us say S derives A, B, A, capital C, and A derives B, capital C, and B derives B, epsilon, C derives D, epsilon, D derives small d, D derives small d, D derives small d, right? So it is very easy to say that the language does not contain epsilon. If you observe it, whatever you do, there will always be BA. If you start deriving from S, there will always be BA. You cannot eliminate BA at all. Therefore, epsilon is not in the language. But then don't use that process, that intuition. Let's use the method which we can apply to any grammar. Okay, let's use it in a systematic method. Okay, which we can use in any language. So what is the systematic method is? Simple. Find out all the nullable variables. Find out all the nullable variables. Find out all the nullable variables, right? So B derives epsilon is there, so B is nullable, and C derives epsilon is there, so C is nullable. Now B and C are nullable, therefore B and C are here, therefore A will also become nullable. A will also become nullable. D is not nullable. Now S is not nullable because even though A and C are nullable, both of them go to null, there will be BA remaining, therefore S is not nullable. So what you can understand from here is epsilon is not in the language. 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 Right? So we can eliminate all the epsilons, right? So what are the nullable here? A, B, C are nullable. We can eliminate all the null productions. How? By writing with it, by writing without it, right? Now see this. S derives A, B, A, C is there. A and C are nullable. A and C are nullable. So write with it and write without it, right? So if I write without A, I am going to get BAC. If I write without C, I am going to get ABA. If I write without A and C, I am going to get BA. I am going to get BA. Right? Right? Now here B and C are nullable. Do the same thing. Write with it, write without it. Write with BC, remove B, write C, remove C, write B. Remove C, write B. Right? 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 Simple, right? Now B derives small b. Epsilon is not required. Epsilon can be avoided. Okay. And C derives D. Epsilon can be avoided. And then D derives D. And then D derives D. So this is the grammar without epsilon productions for a grammar with epsilon productions. There is no epsilon production at all because epsilon is not in the language, right? When epsilon is not in the language, you don't have to write epsilon at all. Now when you try to eliminate the epsilon productions, sometimes you get unit productions, right? If you observe this, A, C is a unit production, B is a unit production, right? So A derives C is a unit production. If I have anything like this, A derives B, if both A and B are variables, this is called unit productions, right? And unit productions are useless, unnecessary. Epsilon productions are useless in most of the cases except the first one, and unit productions are useless. So we will try to eliminate unit productions. Okay, I will take an example and I will tell you how to eliminate unit productions. Okay. Elimination of unit productions. Okay, so what are unit productions? Productions are of the form A derives B. Let's take an example and eliminate it. Okay, let us say S derives A or B derives A or B, A derives A or BC or B, A or BC or B, right? Now clearly there are unit productions. Clearly there are unit productions, but while eliminating unit productions, you should be little bit careful, right? You should not miss out the language. If you directly eliminate the unit productions, the language may change. We have to keep the language as it is, and we have to eliminate the unit productions. For example, SG as B is a unit production, right? S derives B is a unit production. And what does B derive? B derive A and B derive BB. What does A derive? A derive A and A derive BC, and again A derives B, and the same thing will repeat, right? So if I eliminate this epsilon production, I will lose a chance to generate BB, BC and A. That is why eliminate that epsilon production, eliminate this epsilon production, but then add all the remaining things which we may miss out. What are the things that we miss out? BB, BC and A. BB, BC and A we may miss out, so add all of them, right? And again, if you see here, B derives A is a unit production, right? B derives A is a unit production. What does A generate? A generate A generate BC, A generate BC and A generate B, and again this if you go on it will repeat, so stop there. Okay, so if I have to eliminate this unit production B derives A, I have to add A and BC to the B, right? So what do I do? For B I will add A, BC and then BB, and then I will remove A. BB is already there, that is why I'm adding it here, and AB we got from A, right? Now again there is a epsilon production here. A derives B, right? So again there is epsilon production here. A derives B is a epsilon production, right? Now what does B generate? B will generate BB. 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 Right. And B is also generating A. Again, if you go on, it will keep on repeating. A will generate B, B will generate A. You can stop it here, right? Therefore, if I remove this unit production, A derives B, I have to add BB, right? So, to A, if I remove unit production B, I have to add BB, right? So what are the productions we got? This is one production we got without unit productions. This is one production we got without unit productions. This is one production we got without unit productions. Without unit productions, right? Actually A is reachable, but B is not reachable. If you see in this grammar, I will take it again anyway, but if you see in this grammar, from S you are able to reach A, from A you are not able to reach B. So altogether this is useless. You can eliminate this, but that will come under a different problem called elimination of useless symbols. There we will see it, right? Here my intention is to talk about only unit productions. Anyway, this can be eliminated, but we will see that later. Okay, we will see that later. We'll see that later. Let's see one more question. Where unit productions can be eliminated. Let's see one more question where unit productions can be eliminated, right? So S derives AB, A derives small a, B derives CB, B derives CB, C derives D, D derives E, E derives A, E derives A, E derives A, E derives A, right? What are all the unit productions here? Here you can see that B derives C is a unit production. B derives C is a unit production. And what is C deriving? D. What is D deriving? E. What is E deriving? A. So if I eliminate this unit production, B will miss out a chance to generate A. Therefore, add A here and you eliminate the unit production C. Right? Similarly, C derives D is a unit production. And D derives E is a unit production, and E derives E is a unit production. If I eliminate C derives C, you should add A. If I eliminate C derives C, you should add A. You should add A. Right? And then D derives C is a unit production. D derives C is a unit production, and E derives EA is a unit A. We are going to get it, right? So if I eliminate D derives C, I will lose a chance to generate A. Therefore, you are going to write A here, and E derives A is not a unit production. Now again, here also if you observe it, S is deriving AB, which means A and B are reachable, but then this C, D, E are not reachable. You can eliminate them, but anyway that will come under a different topic called elimination of useless symbols. We will see it again there. Even if you are not able to understand here, just leave it for now. I will show you with examples how to eliminate useless productions. Okay, I will show you with examples how to eliminate useless productions. Okay, now let us see how to simplify a grammar. Okay, let us see how to eliminate useless symbols. Right, let us see how to eliminate useless symbols. Okay, 1 minute, I have kept my pen somewhere. Yeah, it is here. Let us see how to eliminate useless productions. Okay, how to eliminate useless productions. Elimination of useless productions. Elimination of useless productions. Sometimes a vertex cannot generate any string. Sometimes a vertex cannot generate any string. String means terminals, right? Then it is useless. Sometimes what happens is, sometimes a vertex cannot be reached. Sometimes a vertex cannot be reached, then the vertex is useless. Then the vertex is useless. Okay. So I'll give you an example. Now you tell me what are the useful symbols here, right? So S derives AB or A derives BC or B derives AB or C, capital C derives AC or B, capital C derives AC or B. Now we have to find out now we have to find out what are the useless symbols in this, right? So first we will find out what are the useful symbols. What are the, or let us say, what are the symbols that are deriving something? What are the symbols that are deriving terminals, right? A is a symbol which will generate A, B is a symbol which will generate A, B, right? Now A is here, A is here, A is deriving something, and S is deriving A, therefore S is also useful. S is also useful. S is deriving A, right? Now B is here, A is deriving B, therefore A is also useful. A is also useful. A is also useful. A is also useful, right? So A is useful, B is useful, sorry, A, B is useful, S and A are useful, right? What about B? B is generating AB, but B is not useful as of now, and C is also not useful as of now. They are not here. B and C are not here, right? And here also C is not useful, B is not useful, right? So only useful symbols are A, B, S, A. So you can eliminate all the other symbols except A, B, S, A. So I will write S derives A. This can be eliminated because B is useless, right? This can be eliminated because B is useless. So A derives B, and this can be eliminated because B is useless. This can be eliminated because C is useless. C is useless, B is useless, right? So we got this simple grammar: S derives A derives B, right? Now if you observe it from S, first we deriving whether they are deriving some useful symbols or not. After that we will see whether they are reachable or not. If you see this, S is not able to reach A. From S we cannot reach A. So this is also useless. So what remains? S derives A is remains. S derives A remains. S derives A remains. S derives A remains. This is how you find out whether the grammar symbols are useful or not. So now let's see one more grammar and we will try to eliminate the useless symbols. Okay. Let's see one more grammar and we will try to eliminate useless symbols. Okay. So the grammar is S derives AB or AC, A derives AAB or BAA or A, B derives BBA or AAB or AB, C derives ABCA, ADB, and then D derives BD or AC, BD or AC, right? Out of all these symbols, which symbols are useful? Which symbols are useful? Right, right. So first let us see what are the symbols which are deriving terminals. What are the symbols which are deriving terminals? Okay. So initially A derives a terminal A, B derives a terminal B. So all the terminals you have to add. Now see on the right hand side where only terminals are there. Here on the right hand side only A is there. Here on the right hand side only A is there, right? Here on the right hand side only A is there. Therefore A is deriving A. So A will be added to the deriving set, right? Now let us see in the right hand side where A, B, A are there, right? Here if you see this, B, B, A are there and B, B, A are in this set. Therefore, B is also deriving something useful. B is also deriving useful symbol. Now you see on the right hand side wherever there are A, combination of A, B, A, B. And here you can see that there is a combination of A, B, right? Therefore, S derives AB. S derives AB, right? And in the right hand side you can see if you can add anything. S is added, A is added, B is added, right? Can you add C? In order to add C, here there is C. C is not useful as of now. C is not deriving anything as of now. And here also D is not deriving anything as of now. In order to add D, Here D is not deriving anything as of now and C is not deriving anything as of now, right? So only these are the deriving things. Only these are the deriving things. Okay. Okay. So this can be eliminated completely. D can be eliminated completely. Now wherever you can see any symbol other than AB, ABS, you can eliminate it, right? So AC can be eliminated because C is useless. C is useless, right? 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 And then nothing. That's it. That is the grammar, right? So what is the grammar without useless symbols? S derives AB and A derives AAB or BAA or A. B derives BBA or AAB or AB or AB or AB. Right? Right? Now, from S you are able to reach both A and B. Therefore, this is the final grammar. This is the final grammar. This is the final grammar. A and B are reachable. See, after finding out whether they are deriving terminals or not, you have to find out whether they are reachable or not. S is reaching AB, so A and B can be reached. A and B can be reached, right? So this is the final grammar after removing the useless symbols. This is the final grammar after removing the useless symbols. Let us see one more example where we want to eliminate useless symbols. Okay. So S derives A, B, C, capital C, B, A, B, A derives A, B, A, C, capital C, A, B derives B, 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 or A, C derives CA or AC, right? So from this, first you have to find out what are the strings that are deriving. Okay, first you have to find out what are the symbols that are deriving terminals. Terminals derive terminals, right? So A comma B are the terminals. I am putting them because terminals derive terminals. Now C in the right hand side, only if terminals are there. Here only terminals are there. Therefore A can be added to deriving list. Okay. Now A is added. Now C in the right hand side, any combination of A, B, A. C in the right hand side, any combination of A, B, A. Here there is A, therefore B can be added. B can be added, right? And here BAB is there and BA is there here. So therefore S can be added. S can be added. Let us see if C can be added. C cannot be added because C derives CA. CA is not deriving anything, and C derives AC. C is not deriving anything. Therefore, you can delete it. Therefore, you can delete it. Okay. Okay. So C has to be deleted. So C has to be deleted from here also. C has to be deleted from here also. Right. Now, what is the grammar we got? S derives BAB. S derives BAB, A derives AA or BAC or AAA, B derives BBB or small a, B derives BBB or small a, right? Right? So C has to be deleted. So here also C has to be deleted, right? Now if you observe it, S is deriving B, but B is not deriving A. So if you see the reachability, if you see the reach, S is able to reach B, but S is not able to reach A. S is not able to reach A. S is not able to reach A, right? So A is not reachable. S is able to reach B, but B is not reaching A, or S is not reaching A. So therefore you can completely delete it. You can completely delete it, right? So what do you get? You get S derives BAB or B derives BBB or small a. This is the final grammar we got. This is the final grammar we got after eliminating useless symbols. After eliminating useless symbols, we can actually represent grammars in many forms. Okay, I think this is the time for a story. Let's go and see a story and then get back to the TOC. Okay, so BVR Mohan Reddy, born in rural Mahbub Nagar, Telangana, with limited local educational resources. He did his BTech from IIT Kanpur, followed by MS at University of Michigan. What are his achievements? He founded Scient. Formerly it was called Infotech Enterprises, now a global engineering services company, and chaired NASCAM, key driver behind India's semiconductor mission. He led one of the India's first global tech outsourcing firms with scale, employment and industrial engineering vision. He is a hero for me. Born from a local poor background, nothing stopped him. He did his BTech from IIT Kanpur. And then he has achieved heights that no one could even dream of. He's a billionaire, right? Jai Hind. So we can represent a grammar. In many ways. Right? Two popular are two popular representations are two popular representations are one is CNF, and the other one is BNF, and the other one is CNF and the other one is GNF. I got confused. One is CNF and the other one is GNF, right? What is CNF? CNF means Chomsky normal form. Chomsky normal form. And other one is GNF. What is GNF? GNF means Greback normal form. Greback normal form. So there are many ways to represent a grammar. Two popular representations are CNF, which means Chomsky normal form, and GNF, which means Greback normal form. CNF and GNF. Okay, CNF and GNF. Okay, now coming to CNF. Let's see the definition. Coming to CNF, the CNF definition is if all productions are of form if all productions are of form A derives BC, if all productions are of form A derives BC or A derives A derives BC or A derives A, where A, B, C are variables and small a is a terminal, and small a is a terminal, and small a is a terminal, which means if all the productions are of form A derives BC or A derives small a, where small a is a terminal, where small a is a terminal, where small a is a terminal, then this is called CNF. CNF means all productions should be of form A derives BC, A derives A. Either it should be two variables or it should be a terminal, right? Where A, B, C are variables and small a is a terminal. Small a is a terminal, right? Right? So, what is the advantage of CNF? In CNF, in derivation process, in CNF, in derivation process, in derivation process, in derivation process, the length of the length of the length of the sentential form, the length of the sentential form, the length of the sentential form, the length of the sentential form always, the length of the sentential form always increases by 1, increases by 1, increases by 1, or terminals increase by 1, or terminals increase by 1. The length of the sentential form increases by 1 or terminals increase by 1, right? 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 So I'll just give you an example. I will just give you an example. S derives AB, A derives small a, B derives small b. S derives AB, A derives small a, B derives small b. Now let us say I want to derive AB. I want to derive AB. Then what happens is first I will replace S with AB. This is step 1. And then I will replace A with B, A with A, A with A, and then let us say we want to generate AB, not AB. Let us say we want to generate AB, right? Then A will be generated by A, B will be replaced by B, right? So in order to generate a string of length 2, we have 1, 2, 3 steps. We have followed only 3 steps. We have followed only 3 steps in order to generate a string of length 2. In order to generate a string of length 2, we have followed only 3 steps, right? So if you observe it, always either the length of the sentential form is increasing or the number of terminals are increasing at any time. See this? The length of the sentential form has increased to 2, or the number of terminals have increased by 1 here and by 2 here and by 2 here, right? Right? And if you observe the number of steps, to derive, the number of steps to derive is 2 into mod W minus 1. The number of steps to derive, the number of steps required is 2 into mod W minus 1. These are the number of steps to derive a string of length W using CNF. Using CNF, if you have to derive a string of length W, the number of steps is 2 into mod W minus 1. 2 into mod W minus 1. ठीक है, ठीक है, ठीक है. What are the advantages? We will see the advantages. Okay, we will see the advantages of CNF. We will see the advantages of CNF. We will see the advantage of CNF. First advantage is length of each production. Length of each production is restricted. Length of each production is restricted. Number two, derivation tree. Why is length of each production restricted? Either it is 1 or 2. If you take any production, it will be of length either 2 or 1, isn't it? It is of production is of length 2 or 1. So you need only 3 symbols to save maximum. You need only 3 symbols. In those 3 symbols, you can save these 2 symbols also. So length of each production is reduced. And derivation tree or parse tree. Derivation tree or parse tree of CNF is always binary. It is always a binary string. It is always a binary tree, right? And the third advantage is the steps required to derive a string of length w is 2 into mod w minus 1. And the fourth step is it is easy to apply CYK membership algorithm. What is CYK membership algorithm? Given a language, given a grammar, does a language, a string belongs to it is a membership algorithm. I will tell you what is CYK membership algorithm. CYK membership algorithm. C means cock, COCKE, cock. Y means younger, YOUNGR, younger. And K means Kasami. 𝐂𝐤𝐴𝐻 Kasami. This is 𝐂𝐤𝐴𝐻 membership algorithm. For this we use CNF. So what is membership algorithm? What do I mean by membership algorithm? Given a string, will it be generated by a given grammar? Given a string, will it be generated by a given grammar? For example, they can ask you in the exam some question like this, right? They may give you a CNF. Like this: S derives AB or BC. A derives BC or A. B derives AC or B, AC or B, C derives AB or C, AB or C, given this CNF, this is a CNF, Chomsky normal form, right? Given this CNF, they may ask you a question like this: AB, 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 does it belong to AB, AB, does it belong to language generated by the grammar, right? So there is an algorithm which we have to apply. Before going ahead and looking at the algorithm, I want to show you one interesting grammar, and also I want to show you the process of how to convert any grammar into a CNF grammar. I want to show you the process of how to convert any grammar into a CNF grammar. Okay, I want to show you how to convert every